Buenas tardes. Buenas tardes. ¿Tienen alguna pregunta, algún comentario antes de empezar la clase?
Hola,
Gusto,
profe,
profe.
buenas tardes.
¿Qué tal? Buenas tardes.
Por mi parte, yo tenía unas dudas del Homework 2, pero te mando por correo mejor, cuando ya
Ok,
tenga más dudas.
ok, perfecto.
Gracias.
Seguro. Bueno, creo que ya tenemos quórum.
Suficiente como para iniciar la clase.
Clase, correcto. Vamos a
¿Cómo está,
empezar.
profe?
¿Qué tal? ¿Cómo estamos?
Completamente aburridos.
Completamente aburridos.
Ya afecta ya estar encerrado. O
Y
sea,
las tareas no los entretienen. Es suficiente.
Lo que la hace más interesante, porque, digamos, ves, uno se ve el ejercicio del Homework 2 y dices, por ejemplo, al menos yo me digo a mí mismo que no cacho ni siquiera que mismo no estoy entendiendo. O sea,
Ah,
toca ver
sí.
los videos, toca ver los videos, toca ver.
Ok. Ya, no, no, y pregunta también, o sea, claro, si, no, si todavía no puedes formular la pregunta,
Exacto.
quizás el lunes vamos a sentarnos, eh, digamos, ejercicio por ejercicio para cerrar, quizás si tienen algunas dudas todavía, vemos algunos, damos algunos datos sobre cómo abordar los ejercicios y entregamos, digamos, 2 o 3 días después. Me imagino que quedan algunas dudas nada más. Ok. Bueno, so yesterday we were discussing the canonical transformation approach, canonical transformation approach to dressing the Einstein phonon. Okay, so we did a couple of canonical transformations in order to address the problem of having. Okay, let me change colors here so it looks more fun. So we have the Einstein phonons are independent oscillators attached to each of the lattice sites. Okay, and the adding the coupling between these independent oscillators, okay, made for dressing, okay, dressing the independent oscillators, okay, and we found the real phonon, or real phonon is, we found that the real phonon is identical to the dressed Einstein phonon. Okay, so that was a very nice illustration of how to solve a problem entirely within the second quantization approach, doing the appropriate transformations. Okay, so now it's going to be, today we're going to do a more fun approach, which is making contact with the previous formalism. Okay, so today, the previous diagrammatics, we approach the problem okay, from diagrammatics. Okay, and it's a less trivial problem than we had seen before. For remember that we had used interactions that commuted with the H0 Hamiltonian. So previously, let me sort of review that. So previously, we had sort of we had addressed trivial examples, okay? Where H1 and H0 commuted. Okay, so that was very easy to solve, although we illustrated that the quasi-particle nature of the new particle, right? So we added, for example, some H1 that only depended on momentum, having H0 as a free the pre-particle Hamiltonian, and then the dressing was very, very simple in that case. Here it's slightly, a little more sophisticated, okay? So here we have that the Hamiltonian is going to be of the following form. We have H omega 0, okay? And this we go all the way back to our formulation in terms of the creation and relation operators of Einstein phonon excitations, okay? So we have BK dagger, BK plus 1/2, okay? And then we had this big term here, okay, which was involving coupling between the states of the Einstein oscillators, okay? And we had this form here, okay? So this was the Hamiltonian that we applied the canonical transformation to, and we obtained the, this is dagger here, and we obtained the exact result. So you see how exact results are very important in physics. So at least so what we call the spherical chickens of the problem, we have an exact result, and then we can use those results, perturb those results in order to obtain more sufficient, more interesting results. 1 second, then we have lots of noise here. Second, let me listen to what they're saying now on the street. The quality of the sound was so bad that the truck was on the other, just outside the window, and we couldn't understand what they were saying. Okay. Okay, so this is the Hamiltonian. So this is going to be now my H0, okay? And this is going to be my H1, okay? And it's clear that now we have these operators imply all kinds of couplings between the wave vectors of the unperturbed Hamiltonian. Okay, so let's see what kind of processes we're going to have here, so that we can inspire our propagator expansion. Okay. So we have, let's expand this term here. Okay, so we have terms going like this. So we have terms in Hamiltonian in H1. Let's put here. Okay, so let's switch to black. Okay, so we have BK times BK minus 1. Okay, so this you see here that here in the Hamiltonian, you can have terms, physical terms, that make two particles disappear. This wouldn't happen in fermionic Hamiltonians, and that's because we cannot destroy fermions, but we can destroy phonons, right, completely. And here we can also create two phonons, for example. So we have this process here. Another process that we can have is BK. Let me put it as an expansion here. So we have another term like this. So BK dagger. Okay. And then we have a B minus K dagger, B minus K. Okay. And then we have another term like this, B minus K, B K. Okay, so yes, I think everything's fine. So this operator here destroys two states. Okay. So this destroys a state in minus K and a state in plus K. Here we create one and destroy one, okay, of the same K vector. here we destroy one in minus k and they create one in minus k, okay? And here we create one in k and one in minus k. Okay, so how do we represent these? Okay, so let me show you this. So we're going to pictorially, we're going to represent them this like this, pictorially. Okay, so we're going to have, for example, the simple propagator, and we're going to determine those. Okay, a simple propagator.
Teacher, what's the meaning of pictorially?
Pictorially comes from pictorial.
The traduction.
And this comes from picture. You know picture?
Yes.
Like a movie, right? So a picture.
Mm-hmm.
It's another word for movie. So pictorially means a diagram in diagrams. Okay, it's another way to say diagram.
Okay.
Okay.
Yeah.
Okay. So we have the simple propagator. Okay, so we'll have something that we'll have to define something like this. Okay, and then we'll have, for example, pictures where we have a propagator disappearing, forward going, and one backward going. Okay, and so this will be k, this will be minus k, and we'll have to draw some interaction. Okay, and this interaction makes disappear. Okay, so disappear in the sense that we have time here, right? Okay, so we have a forward propagating line and a backward propagating line, and they disappear at a certain time. Okay, no more. So we have these two particles here, and they suddenly disappear in time here. Okay, so this would be the KT picture. Okay, and this will represent this kind of term. Both of them disappear, one below and one above. Okay, above the Fermis. One below in minus k, one above, one in plus k. Okay, so this will be represented by this diagram here. So let me put it here. So bk. This would be the bk b minus k term. Of course, this would be this is part of a Hamiltonian where we have this whole thing will be here, the interaction here. The prefactor of this will be the interaction. Okay, so in the sense of a one particle interaction, we have a combination of two operators here, and then the prefactor is the interaction, the coupling between, for example, minus k and k. Okay, so this will be the diagram associated with this kind of term. Then we would have another one which represents now making both appear, okay, one with k and one with minus k. So that we would have something like this. Okay, so suddenly at a certain time, the interaction makes one minus k state and one k state disappear, appear from nothing. Okay, remember that is possible for phonons. Okay, which are bosons, which are massless bosons, which you can make appear and disappear like you do with photons, for example. So, sorry, shouldn't have put the arrow in the middle, but in the end. Okay, so this is time. So this will represent the term that is b minus k bk, okay, dagger. Okay, then we would have terms like this that create one and destroy one, and the other one that destroy one and create one. Okay, so how do we represent those? So this would be a term like this. So we destroy one particle that comes here, and then we have the interaction. So this is destroyed at time t, and then another one appears and propagates forward, the same k. So this would be, let me see. So this would be a destroy one and create one would be a term like this. Okay, the same K, one, you create one here and you destroy one here. And then you'll have the remaining term, which is minus K dagger. Then this would be something that goes like this. Okay, so this would be minus K and K minus K. So with these pictorial representations of what's going on with the interaction, now we're going to be able to write down the form of the form of an expansion, okay, a perturbative expansion in principle, okay. Although you know that the arguments of Dyson, as we have used them before, we always sum, we do an infinite sum here. So if we can sum all the diagrams, we can obtain exact results with an expansion. And they would be valid even if the magnitude of the interaction is comparable to the magnitude of the original, of the H0 term, okay? So what are going to be the Feynman rules? So they will be very much the same as those that we had before. So Feynman rules. So we have, again, IG0 plus, okay? Let's work directly in a reciprocal space where it's nice, everything is algebra, okay? For lines in T plus, okay? And then we have I, G naught minus, okay, omega, the lines, okay, T going in the minus direction, so this will be the K, this will be the K minus K line, okay? And we have the propagator, so we can state, for example, the propagator in the most formal way, the most mathematically correct way, or the most practical way I would say. So this is the time ordering operator with now bosonic bosonic operators here, and we would have the BKT, BK0, okay, and the ground state. The ground state, the interacting ground state. Okay. Remember that we had that the time evolution of a particular operator was done by applying the full Hamiltonian, sandwiching the time independent operator between the exponentials of the evolution operators in terms of the full. Okay, so this would be the full interacting full Hamiltonian. Okay. So remember, we did this exercise exactly for the very simple case. Remember that these are going to be just the Einstein annihilation operator. I think I missed here. I have to put that in here. Okay, so these are the operators that create Einstein excitations or destroy Einstein excitations. And we had done this exercise completely for fermions. And so we can make for problem set questions here. You know that if just following that exercise we did in class, we know that in KT space, we're going to have a minus I theta, the Heaviside function, the exponential. And now instead of having the fermion energy here, we're going to have the oscillator frequencies here in time, okay? And G minus, which is something, the propagator we're going to use a lot here, is going to be now minus I theta minus T, okay? I omega 0. So remember that here when we had fermions, this was the the free electron energies, okay? When we had fermions, okay? This was just the free electron energies like this, okay? Now it's going to be just, I'm also correct. So we just changed here for the frequencies, and we would have now the free propagators, okay? Free propagators, props for Einstein excitations. Okay? So that would be, those forms are very nice, and then we can go and Fourier transform those. We did that also for fermion propagators, and here will be exactly of the same form, but let's write them beforehand so that we have, when they arise in the expansion, we're not, they don't result strange to us. So we have 1 over omega minus omega 0 plus I delta, okay? And we have then the plus corresponding to the plus. So we have exactly the same types of integrals here. So still you have, for example, for free particles in this theory, we also have plane waves as the eigenfunctions. So we will have also the same convergence problems that we had before. So we have to moderate these convergence problems by using the I deltas, and they will evolve to be the lifetimes of the quasi-particles that we eventually are going to obtain, okay? And then we have G minus of K omega, okay? It's going to be minus sign, and I'm going to derive this explicitly so that we sort of do an exercise session in simultaneously, okay? Okay, so let's work out G naught 0. Okay, just so that you feel confident that what we're doing is pretty much the same. So we have, this will be the integral, the same as we did before. So we have minus infinity to infinity, then we have dt I omega t, okay? And then we have the expression for the Green's function in real space, okay? So we have, this will be theta minus t, and then we have I omega 0 t, okay? So this is just the expression of the Fourier transform. So this is going from kt space, which is this expression here, to k omega space here, okay? Okay, so we operate with this this theta function with a minus t, then is 1 for negative t's and 0 for positive t's. So we can sort of build that into the integral, into integration interval here. So this will be minus infinity to 0 dt, and then we can eliminate that theta function, and we put minus I here, and we can take out from here, and we get e to the I omega plus omega 0 t. Okay, and that would be just the integral we have to do. So we do that integration there, minus I, and we get e to the I omega plus omega 0 t over I omega plus omega 0, okay? So remember that I'm going to put a space here because when we evaluate between this between minus infinity and 0, okay, remember that the problem we had is that when we evaluate this at minus infinity, this function is just oscillating like crazy, okay? So it doesn't go anywhere. So what we do is what we add here a minus I delta, okay? And here we have to add a minus I delta. So you see that minus I delta here means that with I times minus I, this it gives you 1, but then delta is in this it's going to be in this interval here. It's going to be negative, so it's negative. It turns into an exponentially decaying function as you take t to minus infinity. Okay, right, so you have, sorry, delta here is positive always, so you have positive, but we have this negative sign here. With this I gives me a +1, but when you take t to minus infinity, then this goes to 0 as an exponential, okay? So in the bottom limit, it's going to be 0, and we get minus I, okay? So we get another I here, from here, and then we get just the evaluation at 0, so this is 1, and we get 1 over omega plus omega 0 minus I delta, okay? This cancels with this, and we get the minus sign that we see here. Okay, so that's the way you would do it for the other case also, and you can derive the Fourier transform just by using what we know about these integrals. Okay, any questions there? Okay, so now let's go to the exciting part here. Okay, and this is pretty much using the same ideas that we use for the polarization diagrams. Okay, but let's make use now of our abilities to add these things pictorially. So in k omega space, okay, in k omega space we have now the propagator, okay, and the propagator. So we make an expansion now, and we're going to use the process. Yes.
Can you put again the last word,
yes,
please? In the denominator, we have omega plus omega 0.
Right.
But
yes,
in the second line, we have with minus.
Well, minus. Here, yeah, sure. Yeah, you're right. Let me see what's wrong here. Okay, because this is because I made this mistake. Here we have, this would be plus here. Okay?
Okay.
Okay? Yeah, just copy it. Okay, so that's the correct form of the...
Yeah, okay.
Okay, thank you for pointing that out. Okay. Okay, so we have the expansion here, and we're going to draw diagrams on the basis of the processes that we already found out that could contribute to this expansion. Okay, so so we have the simple propagator. So now let's imagine what type of first order terms we can have, and the only first order term is related to processes like this. Okay, so we have first order here, and we have also these. But if these diagrams cannot happen alone, because you see that if we have a propagator here, we need to have one line coming, either coming through without any interactions, or we need something where we inject a line and some other line goes out, so that we have a net forward propagator. Okay, so what can happen here is the contribution from these type of diagrams. Okay, so we have K here, we have K here, and K here, and here we have a K. Okay, so we cannot have these type of diagrams because we don't have something coming in, then some process going on, and some K coming out. Okay, so these cannot contribute at this level. Okay, so we only can have this kind of thing, and we can't have this kind of thing yet because by itself it cannot contribute to propagators going forward. Okay, so this is the only first order term that we can have. Okay, and then we can have a second order term related to this one. It's just concatenating two processes. So we have one process like this, then another forward going process. So this would be the first second order process only involving these type of processes. Okay, so K goes in here, interaction, K goes out here, and K goes out here by conservation of momentum, right? So we need to conserve momentum. And this is the only way we can do that. Okay, so forward, forward, forward. And these are the only processes that can happen there. Okay, so now let's try to see, so this is a second order diagram. Let's see if we can make this more exciting by involving these kind of processes here. Okay, or these kinds of processes. So maybe if we combine two of them, we can have something that makes sense. So let's see if we can have something like this. So we can have a forward propagator. Then we have the interaction, okay? And now we can have a process that involves going back in time. So we have minus K, and then we can have another interaction that involves a forward-going propagator like this. So you see that here now we have the type of process that we can have, that we say we could have. So here we have one of those processes here. Made a mistake. Okay, so here we have one of those processes here. Okay, and here we have another one of those processes here. Okay, this is going forward in K. Okay, so you see that this is one type of processes, and this is the other type of processes we have in this. So this would involve one of these guys and one of these guys. Okay, so those are possible with the interaction that we have. So and we also end up with a K vector going in and a K vector going out. Okay, and now we can combine these types of operators. So these are the only second order terms that we can have, and then we can, for example, now let our imagination run wild. So we have something like this. And then we have something like this, and then we take one back, okay, and then we have something like this, and then this goes forward. Okay, we go K, then minus K, then this K. Okay, and you see this is a combination of this guy and this guy and this type of process. Okay. Okay, and then you can combine them as you like. Okay, so let's take, for example, let's do a first summation. Okay, so let's see from this these possibilities here. I'm just going to take forward propagation, just as a first approximation. Okay, propagation as first approximation. Okay, so what will be that case? So we just have these kind of terms. We have forward propagation, then we have, okay, we have this diagram, then we have this diagram here. Okay, so on. Okay, just forward propagating diagrams. And here then we apply the usual tricks. Okay, so I'm going to extract from here, as everything is algebra, we have one, and then we have the interaction line. Okay, plus then we extract here, and then we have the interaction line, propagator, interaction line, propagator. Okay, and so on. So you see now that we get the usual picture where we have this this object here, and then we have the same object here squared. Okay, so we can sum up that series. Okay, and this would give us the forward propagator, and then the usual trick, which was 1, and then we have, okay, this this exact summation, and then we divide by, okay, we divide by this propagator, and we get 1 over the inverse propagator, which we know, again, this is the free propagator minus just the interaction line, like this, okay? So we could now translate this. So this would be IG plus of K omega, okay? And do the exercise. This would be 1, and this would be the IG naught plus to the minus 1 minus, and this I forgot to give, I don't know why, in the Feynman rules we can go back. The Feynman rules, we have the interaction line, okay, is going to be equal to minus I v of k, okay? Okay, so this will be I minus I v k. Okay, so you would put here your interaction, translate this in terms of the functions we found, of the form of the free propagator we found, and we in principle get a first approximation. Okay, first approximation. Okay, this is pretty trivial. I'm going to do now the more sophisticated expansion that you could we can leave for you to substitute here the expressions. Let me put one more detail. Remember that B of k here is going to be from the expression. So B of k, okay, is going to be minus omega 0 over 2 cosine Ka. That is just from the expression of the Hamiltonian here. Minus h omega over 2 cosine. So you should have an h. Okay, so that will be the interaction. You substitute it here. You know, play around with the I so that we get G plus only in terms of G naught plus plus the interaction. Okay, so this I leave as homework, and I'm going to do the more sophisticated case. Okay, so what is the more sophisticated case? Well, now we're going, instead of just doing the approximation of the forward propagation, I'm going to include all these guys here. Okay, so let's remember how we were going to do this. So how we did this. So we go back to full expansion. Adding backward propagating. Okay, G minus. Okay, so let's go to the full expansion here, and I will just do this in detail so that we remember, and it will help you doing the one question in the homework, which is okay. So we get the regular propagator, and now we have the first order term. The only one of which we have is that one, and then we have the second order terms. Okay, this will be the forward propagating one, but then we have the one where we have back propagation. Okay, and then we have combinations of the two, as I was drawing before. We can propagate forward and then propagate backward. Okay, and then okay, so we can have this kind of terms. Okay, so let me so we have this simple term here, And remember that we can have, first I drew the forward propagating, but I could have drawn this like this. So we have the backward propagating first, okay? And then we have the forward propagating. Okay, and so on. Okay, so then you could have two of these, okay, together. So you go forward, backward, backward, and then forward again. Okay, so that would be a third order term. That would also contribute here. Let me just put that one here. Remember that one also exists. So I go. Let me draw the propagator a little longer here, so it's more aesthetically pleasing. Okay, so we go back, forward, back, forward like this, okay, and so on. Okay, so higher and higher order combinations of this. Okay, so remember that now we can combine, and we can combine, for example, these two diagrams here. So we join these two diagrams. Let me make it with a blue line. Okay, so we're going to combine these two. Okay, and then we'll see that we can identify a series of powers. Okay, so let's do it like this. So this will be forward propagating plus, then we have the first order diagram, and we can combine it with the backward propagating. Second order. Okay, and then you see that we would have a combination like this. Okay, and you should sit down and try to convince yourself that there's no other contribution. So you would have to the square of that of this one would be something like this. Okay, so this will be the square of this, and then we would have the other diagram which I drew, which was here. Okay, so this would be forward propagating, then backward, forward, backward, forward, this. Okay, so this would be the square of this one. So this is second order. This would be fourth order. Okay, and there's one. Okay, so there's one way to do this one, and there's one way to do this one, and then we have two combinations. Okay, so let me put it like this: two diagrams where we have a, and I drew them already up here. So we have one that goes forward. Okay. Then goes backward, then goes forward, like this, okay? And the one where this forward propagating term would be on the other end, which would be this one here. Okay, so here we have all the diagrams that I'm showing here. We would have this one, and then twice this one, depending on whether I stick this one at the beginning or at the end of the diagram, they would be both the same because this is just an algebraic expression. Okay, so now we can express this as, okay, the forward propagator, and then we have the diagram like this, okay, plus the backward going one. Okay, and then we would have this same term squared, okay, and so on. Okay, so you see how I reorganize, I join together the two basic diagrams, one which is forward propagating, one that excludes includes backward propagation, and then the rest of the series, and that would be good for you to convince yourself that this is correct. It would be just generated by combining the terms in this way, okay? And this is exactly the same trick that we used for the polarization diagram. So we extract again a propagator here, and we will have now 1 plus just this type of diagrams, and here we would have a diagram that goes like this, backward, forward in time, okay, plus squared, and so on, okay? So now you can identify here what we're going to obtain. So we get this is equal to the extracted propagator, the factored propagator, 1 minus, and then we get this type here. Okay, so this would be the second approximation. Okay, taking only into account these two guys. Okay, so now we can divide again by this external free propagator here, and we get the propagator inverse, and then we get the approximation we had before, which was the simple interaction line, and then we would get something like this. Okay, so remember that in the polarization expansion, we had bubbles in between interaction lines. So this is the correction. Okay, so this will be the simple interaction line, and then this will be a correction to the interaction line. So remember that this we called the self energy. We're just following our steps in the case of the RPA approximation. Okay. And we know that then this we can generalize further by following up on self interaction correction. Okay, so remember that this we would understand as a correction to the interaction line, and notice we're doing everything pictorially here. Okay. So we have that now this expansion we can generalize further, okay, by writing this as, okay, as a first approximation, just the bare interaction plus then the interaction, okay, the first correction, and then you can redo all the arguments with the diagrams now, not only including this guy, but including also the third order term, which would be something like this. Okay, and so, okay. So now again, this is a kind of a recursive structure, right? So we did this in the RPA, RPA-like. This is an RPA-like argument. Okay, so now we can sum up the full expression for the effective interaction. Okay, and we know how to do this. So this will be minus I, the self energy is going to be this double line that I drew here. Okay, and this is going to be the bare interaction divided by 1 minus, okay, the just this basic diagram. So you see that the pictures make us only calculate a single term like this, which is this is the only term we have to calculate in the picture. Notice that in the previous expansion we have so we have the simple interaction, then we have this correction, and then we have this correction Okay, so we extract the interaction here, and then we have just this tail here. So let's suppose we take this term out, so we get this term, and then we get the square of that term, and so on. The usual argument we make. And this is the basic piece we have to calculate here. Okay, so let's calculate this I sigma. Okay, so once we calculate this I sigma, this would be this expression here. We substitute that result here, and we calculate the full propagator. Okay. Okay, is it clear? Any questions up to this point before we go to the math? Okay, so
Maybe
let's
when we math, when
yes.
we say that we will.
Sorry.
When we say that
you're not using your headphones.
Okay, when we creo que ya, a ver.
Ajá.
Ok. Cuando decimos que vamos a sumar en la parte de abajo, quizás nosotros lo tenemos que incluir de por medio alguna constante o alguna cosa que haga que, por ejemplo, la primera interacción, por ejemplo, pueda ser más probable que la otra y otorgarle pesos a cada una de las interacciones.
So I mean, all the elements in this expansion are well defined, right? So this bare interaction line, this is going to be I minus IB of K, right? So we know exactly what this is. We know the mathematical expression because it's a bare interaction. We know that from the microscopic theory. Then this will be minus IBK times the bare propagator times minus IBK. And we're adding this to infinity. Okay, so this is an exact result again. Okay, so we don't need to assume anything. We're not even worrying about whether this series converges. And the marvelous thing about the properties of this series that is not completely understood. I mean, the physicists just take out results and they see, okay, this works fine. I mean, this gives us the correct answers. Okay. Sometimes even when this series diverges, there are some arguments like that you will learn about in graduate school. The counter terms, the elimination of the infinities, is a well understood problem already, and this is when we use things called renormalization. Okay, but here the convergence is complete. I mean, here we know exactly what this answer is. Okay, and we can sum it completely, and using Dyson's argument, this works out fine, no matter how strong or weak the interaction. So okay, so there's nothing that we have to assume here in order to obtain the correct result. This is an exact summation of that series. Okay, and we just have to substitute the values for the bare interactions and the bare or the free propagator, and we get perfectly convergent results. Okay, so when we don't get convergent results, then we have to do something else. Okay, was that your question?
Yep.
Okay. So we have now the self energy, and now this will be the self energy for the interaction lines. So let's translate. We use now the Feynman rules. Okay, and with the Feynman rules, we translate this. So this gives us the minus I sigma is equal to minus I B of K over 1 minus, okay, and then we write down the propagator. Notice that this is a negative going propagator, so we have minus IBK, okay? And then we have the IG naught minus, okay? So, so let's pick a collect here. So we have minus I times I, we get minus IBK on top, and we get 1 minus, and this goes plus, so we get D of K, G minus. Okay? So now let's substitute here. Let's simplify this a bit. So we substitute the form for the propagator. So we know that this minus propagator gets a minus sign. We derive that exactly. Okay, we derive that integral. So we get something like this. So this will be, let me just put all the intermediate steps. So we have V of K, and then I get omega plus omega 0. Okay, we don't have to put the delta because everything converges. So we have that we can take the delta to 0, and we just rewrite this as minus I V of K. Then this denominator goes up here. Okay, and we get omega plus omega 0. Okay, plus VK. Okay, so now we have the self-energy. This is a function of variables that we know. Omega is the eigenvalue in the Green's function approach. This would be the Einstein frequency, the Einstein frequencies, and we know the expression for the V of K that we just have to substitute there. Okay. So before substituting the value of Vk, let's just go back to the propagator expression. So what did we do? We have okay, so this is remember this is the expression for the full propagator here, okay? And we just determined this value here, so we now have to substitute the result into this expression. Okay, so we substitute that result there. And we have that the full propagator is going to be the, just so we already had simplified this. We get the propagator to the minus 1, the free propagator minus, and then we have minus IBK, K omega plus omega 0. Okay, and we get omega plus omega 0. Okay, don't know if you remember the example we did when the first time we did an expansion including backward going contributions. We had something like this, very much like this. So let's now substitute here the form of the, so remember that this is I, G, G plus, and this is going to be, let me keep all the I's, so that it's more convincing. So we have omega minus omega 0, but this is what's a forward going propagator divided by I, okay? And then we get a plus here, and we get the I, V, K, okay? Omega plus omega 0, okay? Omega plus omega 0, plus B of K. Okay, so we're using pretty much the same bits and pieces of expansions we've done before. So now we substitute the value of V of K equals to minus omega 0 over 2 cosine Ka. Okay. I notice that here we should have a factor of h, but we haven't been consistent with the use of h here. We always set h equals to 1 in the expression, say for here, so here I will eliminate the h. You can, I invite you to, okay, to this would be a nice exercise for you to do. Reposition all h's here, which is a bad habit that we have using the Matuk. There's all h's in the problem. Okay, but remember that this was a usual practice also with fermions, because we had, remember that we had something like this, omega minus epsilon sub k when we had fermions. This was energy, this was frequency, then that's the same kind of problem we're having. Okay, so I will set h to 1 here just to be consistent with where the convention of units that we had in the whole problem. And we just have to find out now here, okay, the value of the pole here. Okay, so let me just write one more line here. So let's put this I on top so that we can cancel it with this one and see what the pole is going to be. So this is omega minus omega 0. Then we get a minus I, a minus without the I, bk, omega plus omega 0, and this is divided by omega plus omega 0 plus bk. Okay? So this I cancels with this I, and this is the pole that I have to find out. So let's find out what that pole is. Okay, so the equation would be omega minus omega position value of pole. Okay, so we have omega minus omega 0 is equal to minus b of k omega plus omega 0, okay, divided by omega plus omega 0 plus b of k. Okay, so, okay, and this is equal to 0, so this is the pole, okay, pole. Okay, so we can solve this. This is going to be a multiply everything by omega plus omega 0 plus b of k on both sides, okay, so that we get a second order differential equation. And that equation is very simple to solve. Let me solve it so that we get a complete Cathartic effect. So we have omega 0 plus b of k, okay, times omega minus omega 0 plus minus b of k omega plus omega 0 equals to 0, okay? And then we can see that if we expand this times this will give me omega squared minus omega 0 squared, okay, this times this, and then we get plus v of k omega minus omega 0 minus v of k. Okay, and here we have minus vk omega plus vk omega, so this cancels to this, okay? And so we get now twice minus, okay, so we get omega squared is equal to minus of 2 vk omega 0, okay, plus omega 0 squared, okay. Yes. Okay, so we get we can factor out now omega 0, and we get omega 0 plus 2vk. Okay, and now we substitute the value for v of k. So the value of v of k was in the previous slide here. We substitute this value, so we get omega 0 minus, okay, 2 omega 0 over 2 cosine Ka, okay? So we can extract the remaining term, so we get a familiar expression. These two cancel here, and we get 1 minus cosine K. Fantastic. So now we see that, okay, exact result. Okay, remember that this was the expression for the dispersion that we had before. Okay, so this is the end of the result. Okay, we identified the correct pole for this problem, IG naught. So we identified the pole, and the pole gives us the correct dispersion relation, which is the relation between omega and K. And we get this, this is for the new quasi particle, okay? Okay, which is the, sorry, particle, okay, which is a real phonon or a dressed, okay, dressed Einstein phonon. Okay, any questions here? So we closed the loop, okay? So we did it by canonical transformations, we did the exact result. We knew the exact result because we've done this problem in solid state 1, okay? And we know the dispersion, and now we've obtained it through this diagrammatic form, doing an exact summation of the expansion. Any questions? Comments? No? Okay, so this is actually a very nice project that you could take on for the final report. So let me make the suggestion here. So, suggestion for final report. Okay, there's a chapter in Matuk of how to obtain the ground state, the interacting ground state. Using diagrams. Okay, so that's an interesting problem, and it turns out that we have to sum over all closed diagrams. Okay, so this would be a very nice problem in which you could obtain an exact result using that. Okay, so the ground state, okay, of interacting Einstein phonons. Okay, so that could be a nice exercise to do. To anyone who's interested in this, just write me a line, and I will reserve this problem for you. Okay, so let's go back now and to the electron-phonon interaction. Okay, so the electron-phonon interaction with the material we generated in this simplified, at least low dimensional formulations. We've done this for the linear chain, for example. Okay, and so that we've been able to write the canonical transformations in a very simple way. But now let's go back to the electron-phonon interaction. Okay, let's go back to electron-phonon interaction. And then we'll formulate it now in full 3D glory, okay? so that you get an opportunity to address this problem from the 3D perspective. And you'll see all these expressions that we have done in 1D, we'll do them now in 3D, okay? But not with the, with a more reasonable exercise, as a more reasonable exercise. Okay, so remember that we've had, we have the full Hamiltonian for the electron phonon problem, okay? We have the electron Hamiltonian, which we already addressed in the first part of the course, okay? This is includes electrons and electron-electron interaction, which we addressed before. And then we have here the pure phonon Hamiltonian, which is now the harmonic approximation for phonons. And this just contemplates lots of real phonons, the real phonon problem, okay? So this is what we just solved right now, at least for the one-dimensional problem. And now we have to include the electron phonon term here. Okay, so this involves only fermion operators. Okay, this is going to involve only boson operators. Okay, and this is going to be a mix of fermion and bosons. Okay, so so how do we address this term? So we had started on that. So we have that basically the electron phonon Hamiltonian is going to be a sum, okay, over two labels here that I'm going to call Ij. And then we're going to have a potential, which is going to be a Coulomb potential interaction between electrons, okay, which are labeled by a small r, okay, so this is electrons. Okay, and then we will have the coordinates of the ions, okay, so these are ions here. Okay. Okay, good. So we have this this form. So this will be, for example, for the static lattice. If we have no vibrations of the lattice, we just have this interaction. Remember that this will be just in the static limit, in the static limit. Okay, of the electron gas in a solid. Okay, this was a contribution. Okay, this term cancels with the tadpole. Okay, remember we showed that in class. So this is just the sum, the interaction between the electrons and the ions, plus the ion-ion interaction cancels with the tadpole. So that's why in the for the electron gas description of the Hartree-Fock interaction, only the oyster survived. Okay. But now we want to go beyond that limit, okay? We go beyond, going beyond the static lattice. Okay, then we have to add a deformation. So now the electron ion potential is going to be a function of the electron coordinate, okay? Then the original position, the static position of the ion, which is now displaced by some vector u, okay? So this will be a vibration, okay, vibration of ions. Okay, so now we just take here E ion would be as a first approximation, okay, the expansion, Ri minus Rj, so this is the first approximation. We know this term, we just discussed this term, but then we have to add, okay, we have to subtract in the expansion, we have to subtract Uj. And I told you in a previous class what the general form of the three-dimensional Taylor expansion was going to be. Okay, so we get gradient, and then we get the ion potential evaluated at the equilibrium positions, okay, Rj, and this will be, and then higher order corrections here. Okay, so the electron-phonon interaction is then this extra term here. So we have electron-phonon potential, okay, which was part of the full Hamiltonian, is going to be a summation, okay, over all the deformations of the lattice, okay, times dotted into the gradient of the electron ion potential evaluated. Okay, this is going to be here. It's going to be a function of R. Okay, because we add over all the lattice sites, so this is going to be R minus Rj. And this is my electron-phonon interaction. Okay, so this is how we build an interaction. Now we know that we had ignored this before because our lattice was static, but now you see if there's a deformation, this will generate a correction to the electron-ion interaction, which is of this form here, okay? See this, that this is here a function of the electron coordinate, not of the ion coordinate, because the ion coordinates are all summed over, okay? So this will generate a single body interaction. Okay? So that's that's a whole story on the electron-phonon interaction. Okay, so how do we now write that in second quantized form? Okay, so we'll go rapidly over how we build this, and we'll pick it up next class. Okay, so how do we do this? We're going to use the trick that we learned in 2 classes ago, which is where we have okay, so we have, let me write here again, the electron-phonon interaction. Okay, so this is going to be a sum over all the ion sites. It should be J. Okay, so we have U, then the gradient, okay, of the electron-ion potential, okay, evaluated at the position of the electron with respect to the position of the respective ion, okay? So how do we do this? So here you see that these are, remember that this is an electron coordinate, okay? So this will make for a fermionic second quantized form, and then we will have to second quantize this guy, which is going to be a bosonic second quantization. Okay, so let's do this by parts, because we've learned 2 ways of doing second quantization depending on whether we're treating bosons and phonons. So we leave here the bosonic degree of freedom alone, okay? And we write this as in the general form of a one body fermion operator. So this will be now the sandwich of my gradient operator. Okay, so this will be inside here, and then we have the electron ion interaction evaluated R minus Rj. Okay, and then we have K here. Okay, and then we have to multiply this by let's call this Ck prime dagger Ck. Okay, so this is the second quantized form of a one body, because we have a single coordinate, of a one body operator here. Okay, is this clear? So we just second quantize this interaction, okay, in terms of creation and relation operators. Okay, so now we can do a little more detail here. This matrix element here. What K values am I referring to? So if I'm referring to a lattice, so this is what we imply by the electron ions. So these ions are on a regular lattice. Now these guys are going to be block functions. Okay, that's going to be my basis set. Okay, so this is going to be the integral here in black. So we have the integral over all space. Okay, and these are going to be now my basis functions, which are not going to be free functions. They're going to be block functions. But we know, you know, the block function is just a generalization of the plane wave. So we just write something like this. Okay, so this is the matrix element we have to do, and these basis functions are going to obey this relationship if they are going to be block functions. Okay, so this is a property, okay, block functions. Okay, so we know this, and we just have to substitute this form into the integral equation. After all, we're not going to do this expression explicitly unless we put some potential, some particular potential here. Then we'll have to go all through the integration procedures. But we're just going to write this as a known function. Okay, so I will write it explicitly in the next. Well, no, let's write it here. Okay, so we can express pi k of r, which is one present here, by multiplying both sides by e to the minus ik dot rj. Okay, so we can express now this wave functions in terms of the positions of the ions. Okay, multiplied by some phase factor. Okay, so what we get, let me write in the next view graph. So this would be the total. We can go through the details next time. So that this is what it turns out to be: minus k vector dot rj. Okay, multiplied by the integral of phi k prime, okay, evaluated r minus rj. Okay, and then we have the gradient of the electron ion interaction, evaluated r minus rj. Okay, and then we have the other wave function here. Okay, so we have to do this integral. We won't do this integral, but we just call it, as we say, this is a this will be just a function of k prime and k, which I will call s. Okay. Okay, and so now we have to quantize. Now we quantize, second quantize. Okay, the displacement u. Okay, so the displacement of the ith, of the jth ion, the vector, and the corresponding, we already did this for the one-dimensional problem. For the three-dimensional problem, we would have something like this. So this, in terms of the bosonic creation and annihilation operators, would be a sort of a rather complicated expression, but at the end, it's the same idea we analyzed before. This will be the sum over Q, okay? Then we have this prefactor here. So this will be, I put big M because this is a mass of the ions, okay? Frequency as a function of Q. Then we have this phase factor here, okay? So this is the how we second quantize. We will have also in 3 dimensions, we have a polarization operator, a polarization vector here that tells me in which direction this guy is oscillating. And then we have the combination of creation of the destruction in this case and creation of. Okay, so this would be the analog of the changes we did yesterday for the corresponding between displacement and momentum in terms of creation and annihilation operators of foam. Okay, so next class we're going to substitute this monster into this expression here. Okay, and we will end up with a very neat expression. Okay, for the electron-phonon interaction, and let me just write it down. So we will have the expression of the electron-phonon interaction, second quantized, okay, would be sum over Q and K, then we have the square root H over 2n omega sub Q, okay, epsilon sub Q, a polarization vector, then we get this function I told you before, that once we do the integration, it will turn out to have this form here. So we evaluate these values for the momentum, and then we would have a C of K plus Q dagger, okay, C of K, and it doesn't matter where if we put these operators before the fermions or after the fermions because they completely commute. So we have B of Q A plus B minus Q dagger. And this is the second quantized form of the electron-phonon interaction, okay? And with having set up this, we can do all our diagrammatics and all this. We won't do anything like that. I mean, the most sophisticated problem for diagrammatics we've already done with the electron-electron interaction, but this would be the electron-phonon interaction that you would have, including now electron-phonons. Okay, but you're already familiar with the tools in order to address this interaction in the context of many body physics. Okay, so any questions? Okay, so so we continue next class. Next class, I'll begin with reviewing, you know, any problems you might have with the second homework, so you can turn it in the following days, and you can start working on homework number 3, which we already have. You already have the tools for that. Okay. here in this section, we will be reusing again our tools, our second quantized tools, to address the electron-phonon interaction in the Polaron problem context. Okay, so we're not really going to learn much more. We're going to do lots of exercises in second quantization, introducing the concept of canonical transformation. So we're not going to introduce any more new tools, okay? So I think it's a good context for you to catch up with the previous materials, okay? And address homework number 3, okay? Any questions?
The homework number 3, ¿cuándo vas a subirle, profe?
It's already there.
¿Ya le subió?
Yes, homework number 3 is already in Moodle, okay? But it's still talking about I think, yes, I put it. Yes, I put it, I'm sure. Okay, it's just going to address some particular cases of integrations and some other arguments about the RPA approximation, okay, that we hadn't evaluated in homework 2. Okay, so it was a very nice meeting with you this week, okay? See you next Monday.
Okay, teacher, see you.
Okay, bye-bye.
Hola, profe, nos vemos el lunes. Hasta luego.
Okay, hasta luego.